I think I was asked to talk a bit about our work on quantum categorical quantum foundations, which we were motivated by thinking about the foundations for potential universal quantum programming languages. But at the same time, it's meant to connect to, in particular, topological quantum physics. So if you don't have a formal language access to what I'm talking about, there's a good physics component to it. I think we'll discover some fun aspects about the foundations of quantum physics from very elementary category theory. So I started making notes. I should say that when I was invited to give this course, it was already on a slightly short notice. Maybe for such a course, I started preparing notes. I have a web page here that has the beginning of course notes, but they're not finished. I did not find enough time. We had to write a grant proposal. There was another conference last time, so I don't quite have the fully satisfactory notes that I was hoping I would have. But for the first session, certainly, I think there's more than enough material there that you can go and check out. So it's on a web page here, quantum language via linear homotopy types. If you just Google that term, I think it will show up. Otherwise, full link is up there. Maybe add my name to it and then quantum language. I think this will come. And then, so this is joint work I'm doing at the Center for what's called the Center of Quantum Topological Systems. We have at New York University in Abu Dhabi. I think this is Hisham Sati, who is the head of the center. And so maybe some of you may know me from my research in past times. So we started doing more abstract algebraic topology related to higher topos theory with applications to string theory. We're trying to find out what are certain higher structures in fundamental physics. But then at some point we discovered, so we were thinking about what is it really like on a mathematical level that it is what people mean when they speak about brains, specifically in M theory. And so we were looking, so we had an idea of how to formalize it. So it's called hypothesis H, a proposal for how to formalize it properly. And then we were looking at examples of that proposal. And it turned out when we looked at certain special cases of brains, defect brains, other codimension 2 effects, that we saw anionic effects of the kind that people think are necessary for, and I'll say a bit about this in a moment, are necessary for making the idea of quantum computation an actual reality by stabilizing the very fragile quantum states by topological data. And it's through this route, kind of discovering anionic, what's called topological order and solid state physics in string M theory, that we came to this topic and eventually started in full research center on quantum topological systems. So that's kind of the story behind this. But let's just dive in maybe. So I'll start with these notes. I'll do some stuff on the board, but I have some notes that I just want to kind of show in parallel. I'll zoom into this here. Let's make this go away and make it large and start. I want to start with some motivation, if you will. So the main part, so the core of what I'm speaking about, like the technical material that I want to present, is an extremely elementary category theoretic analysis that we made in an article called The Quantum Monadology. So I mean, maybe I'll get to speak about some other things too, but if you wanna look up, if you find some of the things I say here in words maybe incoherent because I misremember or forget something, then this is the articles or the archive together with Hisham Sati. And it's effectively the core insight of that article, which I would like to present in this lecture, but with some motivation so that it becomes a kind of fun thing to think about. And so let me start with this motivation, if you allow, before we get into some very elementary categories here. Maybe I have occasion actually for those who, because it seems I just learned also this morning together with Tobias actually, that many or some participants do not have background in categories. And I'm trying to, the way I'm presented, I will talk about data. What does it mean to have data types in a programming language? And that's actually a way to motivate the notion of a category in the first place. So maybe, with a bit, maybe slightly stretching, we might be even able to motivate the concept of category here from scratch. But first, let's do some physics or even application style motivation for the abstract nonsense that will follow. So currently, this is actually quite applied. So there's a So I'm starting with the motivation, where suddenly there's a whole lot of money involved and people are really excited about. And I can tell you from having spent some time with it now, that there's actually major theoretical gaps underlying this whole scheme. Everybody is trying to rush forward to impress the funders with the next invention that will make them keep funding them. But by doing so, people actually forget to look at some foundations, what it actually is that they're talking about, which leads to funny effects where whole groups of people do things that haven't been proven to work and that end up not working. And then it leads to a very confused state in the field. Maybe anybody followed the news just the other day. It was another announcement of Microsoft doing something, which I don't think they did. I don't think anybody understands what they were actually trying to do. So this is related to quantum computing. So some people call this the second quantum revolution. The first quantum revolution is sort of what happened after the 1920s when quantum theory was born. Then in very rapid succession, in the 50s, people started making use of quantum effects. The transistor that is now governing our entire lives, so the computers, lasers were on, and lots of other things. These are quantum effects, but they're still operated on what's called macroscopic scales. So in a transistor, it's kind of important that what happens is an effect that affects a single electron. It tunnels or does not tunnel from one band to the other. But when you actually operate a transistor, it's like a macroscopic number, a huge number of electrons doing that at a time. And in a laser, of course, it's kind of important that in some sense or other, you're actually handling single photons, very quantum objects, but it's still billions and billions of these photons at a time that make up the laser light. And what's now called the second quantum revolution is when people are trying and have shown that they can manipulate a single quantum system, what's called qubits. So not just macroscopic numbers of them, but really single ones. And so what's called quantum circuit computing maybe is, if you wish, the coherent arrangement is the programming of individual quantum processes on finite dimensional Hilbert spaces. So that's the focus actually of what I'm going to speak about, even though I say quantum all the time. There's an implicit restriction of everything I'm going to say to the finite dimensional Hilbert spaces, or rather, I should actually say it's not so much that the finiteness is important for most of the constructions. It is important at some points. What really matters is we will not be considering analytic structures. We're just not considering completeness structures. So these are Hilbert spaces only on finite dimensional vector spaces. Much of the formalism works for infinite dimensional vector spaces, but then it kind of misses the completeness structure, and then it's not clear if you really still want to call it quantum. So in that sense, it's finite dimensional Hilbert spaces, which is what some people call this is digital quantum computing. And I should say at this point, maybe for those not interested in computing but interested in quantum physics, is when I was taught, as studied theoretical physics, we were taught quantum physics. We never saw a finite dimensional Hilbert space except maybe as some toy example, like the spin component of an electron sits in its own little Hilbert space. It was all from the get-go. We were all concerned with this infinite dimensional Hilbert. This was really part of the game. Dirac delta from here and there, right? And one of the interesting insights of the recent rise in the last maybe 20, 15 years of quantum information theory is the insight that there is something of interest in the sector of finite dimensional Hilbert spaces, which is like, if you had asked me as a student after I had the course in quantum mechanics, is there any interest in it? I would have said, well, no, you're throwing away, like investing all this energy into understanding the infinite dimensional case. And now what else can there be actually in the finite dimensional case? So it was kind of a shift of focus. And for instance, it's interesting to note that only after quantum information theory became a thing, did people, for instance, discover what is now called the quantum teleportation protocol, which is the observation that there's in some sense, which by sending some classical information, you can kind of exactly copy a quantum state from here to there. The interesting aspect of this is that it uses exactly no new insight that wasn't already known to the founding fathers. Like Schrödinger would have understood the proof of quantum teleportation, and he would have realized probably that it was a big deal, but nobody at the time realized it because they were just not, because it's a finite dimensional Hilbert space thing. It's just somehow not what people were thinking about. And it's this is a good example, I think, of what we will see, that just looking at quantum physics in this realm actually does have some interesting lessons, even apart from quantum computing, for just understanding foundations of quantum physics as such. So this is something that very much exists at this point, even in toy form. There's the quantum computers that currently exist, they're so-called NISQ machines, noisy intermediate scale quantum computers. They work for a few microseconds and then decohere. But in these few microseconds, they do execute these quantum circuits. So they, in a controlled fashion, more or less controlled fashion, manipulate these bits. But what is eventually what people actually after is what might be called universal quantum computation. And that's where the category theory really becomes more important, is where this coherent aspect is embedded into a classical computing backdrop that controls and is conditioned on quantum measurements. So where a classical machine may be coupled to a quantum computer, the quantum computer makes some quantum processes resulting in some quantum measurements. The classical computer reads out the measurement results, which are non-deterministic. So it kind of uses the quantum computer as a kind of oracle producing some output, and then based on these results, initiates other quantum computations, for instance. In the current scheme, yeah, maybe I'll come to this in a moment. So what is the title of this talk about? Quantum language. So on a broad level, if you're not interested in computing, you can read it as asking, well, what is good categorical general abstract language for talking about quantum processes that are coupled to classical processes, that are controlled and conditioned on quantum processes. But in a more concrete fashion, and that's probably what's written in this article actually, we can ask, well, what is a programming language that will actually, so these things don't really exist yet here, these universal quantum computers with lots of classical control. But once they exist and you want to actually put them to commercial use, you will have to have some rather sophisticated languages to control them in a reasonable way. And so the question is, what is a quantum programming language for these tasks? And so it's effectively also you need a formalization of the quantum theory on these finite dimensional Hilbert spaces. So this is just a side remark which concern us here, but currently there's huge interest in this because there is this promise that it has potentially enormous compute speed ups for certain problems, like the Schwarz algorithm. So like on paper, if this thing would work, it would crack the current encryption protocols due to something called Schwarz algorithm. But in practice, this is decades, if not longer, ahead, actually. But this is what drives an enormous interest currently. But in any case, even if we're not interested in these practical applications, there's insights, as I said before, a couple of times already, into fundamental physics here. So here's two practical hurdles, which I'll take as motivation for developing theory. I think this is a fun thing to have an actual practical problem to which the theory we're developing actually does apply. So there's actually an intrinsic tension in what is called quantum, the current model of quantum computing. There's an internal contradiction which really makes you worry, should make you worry that this thing can work. Namely, if a quantum system is such, like some spins and some atoms that you have trapped in a laser and how you want to control them in some way. If you can control them, they're amenable to local manipulation and observation. Well, for instance, if you make sure that they're coupled to the electromagnetic field, so that shining a laser light on it can swap the spins in a controlled way so that you can arrange a computation of them. Well, if that is the case, then also all noise in the electromagnetic field couples to these spins and decoheres them. So the intrinsic tension is to operate your quantum system, you want it to be interacting with the environment being you, being the programmer, actually programming it. But due to the fragile nature of quantum states, any interaction with the environment leads to what's called decoherence. It leads to the devolvement of the actual quantum property that you want to retain, and that leads to the fact that we have, for instance, already 15 years ago, there was a quantum computer that factored the number 15, 3 and 5. That was maybe not so impressive as a number, but already 15 years ago, this was done. The reason is this was done on spin resonance systems, which have the property that they're actually coupled very little to the environment, which means they're quite stable actually, and you could do it back then, but it also means they're extremely slow. You cannot actually manipulate them much because they couple so weakly. Anyway. So there's two strategies here, and both of them connect to the theory I want to discuss. Subversion strategies. Two strategies to get around this paradox. So one is the one that is most prominent at the moment, like sociologically. It's called quantum error correction. So one induces a high redundancy, as one does in classical error correction. In a single piece of information, you distribute it over many loci of information called qubits here. And then you, in a very clever way, you keep measuring in a good way, so not to destroy the coherence that you actually want to retain. You measure this ensemble of qubits to detect if some of them, if the main information may have decohered, and if so, if you detect what's called a syndrome, that some decoherence may have happened. There's a clever way of having the classical computer initiate another quantum process that kind of fixes this with some probability at least, so that the whole thing works with some probability. That's quantum error correction. It means that you need a very intensive interaction of a classical computer with your quantum system. So there's theorems called the famous celebrated threshold theorem, which says that this can work in principle. So it's a rigorous theorem, under some idealized assumptions, of course, that says, well, if you can bring your error rates down to a single physical qubits down below a certain level, then it's possible to introduce enough redundancy to scale up your system, make it ever bigger. In principle, also have ever more protected qubits. But if you plug in the actual numbers, you get insane results. You see that you will actually, on a tiny quantum chip, you will have to connect it to a supercomputer, classical supercomputer, that is all occupied with just quantum error correcting the quantum computer. And at the same time, the data exchange, these syndromes going back and forth, need to have such a huge data volume that you need to connect your quantum chip to a huge cable, which emits this enormous amount of data, which is the least thing you want to do with a quantum chip. It wants to be sitting in a vacuum chamber at a very small number of, close to absolute zero. So you do not want to connect it with a big cable to the outside world, which is heat carrying. So if you plug in the actual numbers, for the current proposal of this QUAC, it seems quite insane, but this is what people are currently thinking should work. There's another salvation strategy, more fundamental, going, I shouldn't say, going more to the foundations of things, trying to fix problems right at their root. It is to utilize quantum states that just don't have this problem, that they're locally disturbed by noise. These are called topological. They're somewhat non-local quantum states that are intrinsically protected against noise. I can maybe, depending on how time works out, I could say a whole lot about these things, but maybe at the end, just to mention that this exists, and there's good arguments that in the long run, this alone will not actually work, and for the real deal, so right, as I just said, currently almost all credible activity goes towards cracks, but TQC is plausible for inevitable. So in any case, the upshot for this talk is, or for this course, is that both of these need better language, better theory. Both of them need much more fundamental development for commercial scale quantum computing. So one issue with QUAC is that one can, so as I try to make plausible, following this procedure, even a simple quantum will become hideously complex once it's embedded into this quantum error correction mechanism with a complicated interplay, non-deterministic programming interplay with the classical computer. And one problem is that you cannot debug quantum systems due to the fact that there's this thing that whenever you observe a system, its state collapses. So you cannot halt your quantum computation and inspect the registers to see if everything is still all right. Because, you can, but the moment you do this, you've actually collapsed and thereby destroyed the actual quantum process. So the time-honored, there's still, of course, something that is called certifiable classical ordinary software certification, but it's used rather little. It's only used in very specialized industries, like maybe in cryptocurrencies now. Some companies use it where it's really critical that you're absolutely sure that your program does what you think it does. But there's good arguments that if you have full-scale quantum computation running, you need to be able to certify the correctness of your software ahead of running it, because there's no way to fix it kind of on the run. And that means, so I'm not sure if I really get to this point much, but the way to certify a programming language is to have it have, it has to reason about its own data types. It needs to have what's called identity types. And that's really where homotopy types, which appear in the title of this course, appear. So there's some deep math really related to the fact that your language, you want to set up your categorical language for the programming language, certified. And then for the TQC part, it turns out, I say it maybe somewhat vaguely here, but it turns out, as one can maybe see with what Microsoft is doing, that there is quite a vague idea of what it actually means to have these these topological ground states, what it actually means to have them, to operate them, to observe them. So it needs just a better formalization of what is topological quantum systems in the first place. So both of these are theory questions and language questions in the end that enter these practical problems. And to motivate this course maybe, so one question that I will maybe aim for have answered by the end of this course on Thursday is the following concrete question. So this is by design phrased in a language which I'm thinking might pique the curiosity of some purely physics interested people in the audience here. But that's the kind of question we will actually be able to answer in a somewhat interesting way, I think. So here's the question. So suppose we have one of these. Of course, I haven't really explained these things, but maybe it's enough to see the bigger it is. So suppose you have one of these quantum materials that are topological, or technical terms that are topologically ordered. So they feature in some sense their Brown states that have this topological protection, whatever that will mean. But as the name suggests, actually, somehow, technically by definition, it means that the ground state sector of these materials will be governed by topological quantum field theory, which I think we can assume that most people are familiar with, and hence with some form of a generally covariant QFT, like quantum gravity, right? QFT is generally covariant, and so in such generally covariant systems. So mostly this is some forms of Chern-Simons theory, of abelian Chern-Simons theory that is being used here. It's not actually so self-evident to know what exactly the observables are, given that what the symmetries are. So in particular in such systems, there's diffeomorphism symmetries, so this is how we do this here. Systems are diffeomorphism invariant, but part of the diffeomorphisms are bulk diffeomorphisms that are not meant to be observable, that are gauge diffeos, whereas the restriction of diffeos to boundaries, which in an experiment are actually typically the actually observable parts of your material, are actually acting on physical states. So the question is, and this is quite you see, even though it's motivated purely in some sense from asking what is a good theory actually of handling topological qubits, it's actually a question that you can ask much more broadly for all kinds of physics scenarios that are being actively discussed, of course, these days in theoretical physics. It means what is the most usefully pedantic, and by pedantic meaning well formalized, so that we can actually, we're not just talking words, but we can actually make the words precise enough to have a programming language that can actually handle some algorithm. What is the most useful pedantic description of quantum measurement that applies in such systems? What does it actually mean? What is the collapse taking place? Where do these things select? And so over the first maybe 3 lectures, I'll work my way towards quantum measurement in a very elementary setup of just an ordinary quantum systems. And then once we have that formulation, we'll see that it actually generalizes to quite non-obvious systems. Okay, that's a bit of motivation. Maybe there was too much motivation. So here's the synopsis of how we're going to answer these questions, just to give you a kind of, to mention some buzzwords that so on the next slide, from the next slide on, I'll start to actually explain things in detail. But before we do that, let me just mention a bunch of buzzwords here, maybe to put you in perspective. So how are we gonna? What's the solution that I'm going to offer to these problems? So I'll start with the following observation, which is a classic observation that I'll actually review for the. It's easy to see. I'll review it just in a minute. So there's something that some people like to call the grandiose name classical computational Trinitarianism, whatever. So it means that classical logic, and by classical, I should say, I mean, whenever I say classically, I mean as opposed to quantum. One has to amplify this because when you speak about logic, as we will be doing in a moment, of course, in logic, there's also classical as opposed to it's called constructive or intuitionistic, where you exclude the law of excluded middle or the axiom of choice from your logic operators. So that's not what I want to mean by classical here. So I'll sometimes say constructive, but otherwise. Classical logic and functional programming languages. So functional programming language means effectively something like languages where, we come to this, where with every data type, you for instance have also the data type of functions between these data types. They have what's called operational semantics. So they have an interpretation. You can ask, well, if you write down a quantum programming, an ordinary programming language on paper, what does it mean as a mathematical operation? What is this thing doing, but not yet in a machine, but just in mathematical language? This was called operational semantics. And it's a classical statement to be reviewed in a moment that, for the adjectives possibly added. The semantics is what's called locally Cartesian closed LCC categories of classical data types. So that's what I just promised 5 minutes ago. gives us an occasion maybe to introduce categories in the first place. Namely, these languages are fully typed. Then all the data that ever appears is all assigned to a certain data type. And programs are maps between these data types that are the morphism of these categories. So this is a very classical, in the double sense, classical story of how programming languages work. And classical logic works. It has to do with locally Cartesian closed categories, which we think of as the categories of these data types. So the question then is, well, if this is so well established.
Sorry,
please.
Is the Trinitarianism here to do with the Curry-Howard isomorphism, or is it just the
that's actually what. So the three things is, I wanted to draw the diagram. So it's logic, classical logic. It's type theory as a theory of programming languages, and category theory. That's the three things: logic, type theory, category theory. And actually, I see it. We see it on the next slide. That the Curry-Howard isomorphism that translates us from logic to certain operations in classical data types. So that these three things are really somewhat just different aspects of one of the same structure. It does not have another name apart from these three. That is Trinitarianism. See, it sounds a bit overblown, but it's quite a profound statement. It's a bit like a Yoneda lemma statement. It's very tautological in a sense, and yet more important. So this is our starting point. We just ask, well, okay, so now we want to bring quantum in. We don't want to replace it by quantum. We want to generalize it so that quantum processes are added on top of this. That's kind of important. And that distinguishes what I'm doing here from other quantum languages that you might currently be able to, say, download on the web. There's Qiskit by IBM or something where people draw essentially these coherent quantum circuits and tell the computer how to send the qubits through certain quantum gates implementing unity operations. So these are purely, if you will, I would call it coherent quantum operations. They have no classical interaction. It's just essentially a way of declaring linear maps. You have an input Hilbert space as an output Hilbert space. You declare a linear map between them that is composed by the string diagram calculus that we've seen in the previous lecture from certain elementary maps that you call them your quantum gates. So that exists. But what we are asking is how to make this interact with the classical world. What does it mean to make a measurement in such a circuit? And then depending on the measurement result, which is not known during compile time, it's only known at runtime. It's quite fascinatingly, one thinks that this is a completely elementary stochastic process, like not described by any hidden variables. You run the computer, the quantum computer make this quantum measurement, outcomes completely previously non-determined measurement result, and depending on that result, you want to have the quantum computer, the classical computer, decide how to continue with the quantum computation. So how do we add quantum to this picture? And the answer I want to present is that we're going to fiber the quantum data types over the classical data types. There's this little, very fond of this little graphics here. This is my quantum microscope. So very much like in the historical picture where we see a classical world, but we do. But if you apply a large enough microscope, some physical experiments, some electron microscope maybe, or even a particle accelerator, you zoom in to these classical looking things, which for us will be classical data types. You see that around them are actually quantum effects. It's quantum data. And so the answer that I'm going to present is in a we'll go down to a very simple elementary statement is that sort of the quantum analog of this computational Trinitarianism is that combined classical and quantum logic, and hence universal. Remember, this was about classical control. They have a universal classical computer in quantum programming. Have such operations, semantics, and categories that are categories of linear data types fibered over classical data types. So that still sounds maybe somewhat overblown what it really will mean. So we will really just be looking at categories of just vectors bundles over sets for the most part of this course. Where the vector spaces are the Hilbert spaces of quantum mechanics, but we parameterize them over sets. See how that depends on parameterizations affect the whole thing. So this will model classically controlled quantum data. And so then the interesting aspect, and this is where the monadology comes in. The interesting aspect is that by just starting with such a simple category of fibered linear data types, it turns out that just systematic unwinding of the definable monads, I'll explain this, on such quantum data reveals, well, I write all, maybe very much you might put there, but it's actually, I think, basically all. Quantum effect. So we'll say that quantum measurement drops out, the state collapse, so that the Born rule comes out. as all these incarnations of actually known operations that we can do on parameterized linear types. And then, so this, I hope to get here by, by the end maybe of the third talk. And then the interesting thing is that once we've set up in a very elementary fashion this categorical language for handling ordinary quantum processes, we'll see that now that we have this abstract language, it's very easy actually to boost the category to what's called a higher category. We just boost the sets of quantum of the classical data that we've been talking about in the vector spaces to groupoids and higher groupoids and chain complexes fibered over them. It's very obvious once we're here how to do that. And then very interestingly, all the conclusions, because they were abstract conclusions, they will still apply. But then we can see that now that the parameter space, the classical parameter space, are actually groupoids, such as, for instance, configuration space of points of defect in a topologically ordered quantum material behaving like anyons, then the dependence on quantum systems on these defects will mean that there are certain what's called adiabatic Berry phases implied, that the quantum states will transform as you move around in this groupoid. And so we'll be moving to higher classical data types, namely what's called homotopy types. And it turns out that will capture what in physics are called the topological quantum phenomena. This is a common thing that most, if maybe not all, but most occurrences of what physics call topological, is in topological field theory, is actually what in math is called homotopy theory. So this is really the same word here, or the same idea in different words. So quite generally, and that finally brings us to the title of the course, with dependent linear homotopy types, we're verbalizing topological quantum data in quite some generality. Okay, so that was maybe too much motivation introduction. Now let's get going. So I'll explain what this. But maybe, I don't know, is there any question at this point? I haven't really said much. Okay, so for the moment, probably for the rest of today, I'll just be talking about classical language and classical computation to set up the scene, and then we generalize to quantum next time. So the simple but far-reaching paradigm of data types, and that got truncated to just types. So when people say type theory, it's really originally the theory of data types. It comes from the question of what is it actually that programming languages are dealing with, types of things. So the simple but far-reaching paradigm that all data D is we have some type, capital D. So you know this from if you ever played with any computer, there's some basic programming. You have a string, right? You want to encode a string, and you say, okay, I have a data type of type string, and do I encode an integer? You say it's an int, or it's a Boole. And the idea is to do this very rigorously to all kinds of things. And so a program, this gets us really to the idea of a category. So you envision that you have some input data type. Think of strings. You read in some input that a user types into the computer, then a particular datum, a particular string is an element of this type of input data. And the program, if it's well typed, it will take this input data and do something to it and maybe spit out a number, right? You ask it, which day is it? And the computer spits out the day of the month or something. And then it has to have a specified output data type. So a program, in this sense, in what's called a fully typed and fully data type language, is a map from one data type to another data type, which we think of as transforming data of the input data type to data of the output data type. Now, of course, these programs can be concatenated. If you have another program that reads in O and computes something else from it, you can post-compose it here and have a total program that goes from input to output to the next output. That composition is associative, and there's the programs that don't do anything. There's the identity, the trivial programs on O, reading in O and outputting the same O. And effectively, that kind of structure is the structure of a category. So it's an abstraction of the idea of a processes that have specified in and output types, go between these types and can be composed in the sense that you expect things.
The diagram should be output at the type, right?
Oh, okay, that's a typo. Yeah. A typo. Yeah. Thank you very much. There may be more typos actually. I'll go and fix them. Thank you very much. Yes. Okay. Okay, so that's the category for us here. That's the categories where that's the categories you should be maybe thinking of. objects are data types, and between them we have these programs or these maps. And so the idea is then, well, so the idea is to go and strictly specify. You never have data that is of an unspecified type. So what should this type specification entail? Well, it should say what is the admissible, what do you need to provide in order to construct data of some type, and how do you decide if you've given data that is of some type? So the way it proceeds is, in practice, there's a very small set of kind of primitive data types, and the rest are built from so-called type formation rules. And they correspond, I'm being a bit schematic here, but this is really the idea. They correspond to what in category theory are called the universal constructions that you can have in a category. So here's one of the most basic examples. Suppose you have an example of how to build new data types from old data types. So suppose you have two types of data, L and R. You want to build a program that operates on pairs of them. So you want to say valid input of my program is a pair of these things. Well, then you need to say, well, I need a data type of pairs whose elements are pairs of data. I mean, it's all tautological, but it's maybe important if you haven't seen this kind of tautology before to go through it once. So we say data of pair type, we call it L, R in anticipation of the fact that it should really be a pair. And we write the pair type like this as a product. It's constructed all by providing data of this type and data of that type. That is kind of the rule of what it takes to construct. And if you've seen a categorical Cartesian product, of course, you know that there is its universal property says exactly this kind of thing, that you have a program with output L times R, hence to have a morphism, a map, ending in L times R. It's the same thing as having two programs, one with values in L and one with values in R. It's very tautological, but it's an important thing. So this is going in the direction that this data type should be, its operational semantics should be the actual categorical Cartesian product. And then conversely, I'm not going to talk about it unless you force me to. It's extracted conversely by retaining either. So this just means there's projection maps out of the Cartesian product to L and to R. So that if you have data in here, you're able to recover from it precisely data of L and data of R. So in short, well, I mean, not just in short, but to make this precise, you open a type theory textbook that gives you the precise rules. They come down to essentially the statement that the categorical semantics of a pair data type is the Cartesian product. In type, so type is, do I say this anywhere? Type is my notation. This is a slightly unusual notation, maybe, but I'll use this. If it doesn't have a further subscript or superscript, I use type for this category of data types. As we just heard in the previous lecture, categories are often, not always, the exception proves the rule, named after the object. So it's a category of object data types whose morphisms is called as processes are objects. So continue reading here maybe. So this was one example. The other core example is that of function types. So this is something maybe if you've done just most elementary programming. This is something that even some famous programming languages do not support. This is kind of the hallmark of what's called functional programming languages. This is certainly the generality that we are interested in. So there you want to say that whenever you have data of type L and of type R, a pair of data types as before, well, you somehow want to be able to speak about the type of all functions from L to R. So you want to give the collection of all programs that take L as input and R as output. All these programs are supposed to be one data type so that you can hand one program another program as input, for instance. Say, right, take the program that iterates stuff, say, iterate this program for me. So this is an important construction, what's called high-level programming, that you are able to handle programs themselves as data. And in fact, as I'm already saying here, the fun of the typing paradigm is that you strictly and relentlessly apply it to everything. You never stop not typing anything. And we'll see that this has some really interesting consequences. Anyway, so programs are data. This may be the von Neumann principle even or something. And as such, should have a data type. All right, so how is this constructed? Again, it's a tautology, but let me just say it anyway. Well, how do you produce it? Well, you need to produce a data of type R, to be called f of L, for each datum of type L, which is a function, right? For each of these, you need to And if the extraction, I'm not sure if this makes sense to anybody. I haven't really explained the elimination rules here, but how to extract data. Suppose you have data of function type. Well, then to extract data of type R, you should be able to feed data of type L. So this is just to give an idea of how we specify new data types from old ones. And we'll see in a moment that it's actually not. You might ask, well, how many rules are there maybe to construct new data types? We'll see in a moment that these rules are being picked from a very ancient set of possibilities. Maybe these are just the rules of logic, really. To see in a moment, that's where the Brouwer this type should come in. So then when you have these types, it turns out you can derive, there is it's called the deduction rule. So if you think of this from a purely language theoretic or type theoretic aspect, then in that language, there's rewrite rules that make the computer know from which kind of language constructs other constructs can be produced. And remember this funny notation, this is the way it goes. This funny Johnstown symbol here for denoting programs. If you have a program that reads in data of pair types and outputs something where I'm distributing the two datums here, all of the subscript along with that argument to indicate that we think of this as maybe a background flag. This is something that is like an input to our computer, but we want to regard it as not maybe the user specified input here. This is just a cosmetic thing. So we put it as a subscript, maybe a flag, maybe that we put in our program. It does depend on it, but it's maybe set by the programmer. And then there's actual input. So if we have a program that takes pairs input that produces an output, well, that should certainly be this, or from this, we should be able to produce a program that as input takes just these flags, and as output puts out the program that we just defined as a type here, right? The program that is the resulting program that for that fixed flag, gamma, outputs the given function from L to R. So it just curries, uncurries one of the variables. That's how the technical term goes. A function of two variables is the same thing of a function of one variable with values and functions with the reading in the other variable. And so, funnily enough, this is a historical coincidence as far as I know. This notation here, which is traditional notation for rewrite rules, telling the type system that this can be rewritten to that, is exactly a corresponding notation that is traditional in category theory. So remember the operational semantics of this. So we have just a map from morphism of our category from here to there. And we want to say, well, there should be this function type here, which right here now, I don't know if I introduced this before, maybe I didn't. So in category theory, this function type, of course, right, the internal home has different notations. Some people write home underline, but one notation is a square bracket, which is maybe reminds you of maps from L to R. So
excuse me. So square bracket is the old.
That's the internal home, yeah, internal home. So this is an object in our category, which exactly satisfies this property that maps from any gamma into it are a natural bijection to maps from the Cartesian product to R. So that is what characterizes this object. And is the function type. Yes, this is the rule for the internal home. So that's why I call it here this is the adjoint. So we say that the notation is that taking the product with L, left adjoint. So unfortunately, this is also a Johnstown symbol, which is completely unrelated or unrelated. This is left adjoint to, well, one way of solving this is to go like so. Which is probably what I do most of the time. So here's our category. And now there's so this is the categories. Remember, object are data types and arrows in there are programs. There's also a map from this category to itself. Also an arrow in the category of categories, where this is the operation of taking any type and forming the product data type with L. Can you read this if I write here? Does this work? So, and there's another functor, which is the one here, that forms the internal home. So this is the functor that takes any type, forms the data type, and forms the type of programs from input data L to the given one. This also gives another type of what we just said. And we say write this symbol down. Say this functor is left adjoint that functor. So this is an adjunction. What does it mean for two functors to be in a junction, to be in a junction to each other, whatever? It means really this. There's a natural isomorphism between maps out of the images of the left functor, for us crossed with L, maps from that kind of thing, are natural bijection where one has to think about what that means. You can figure that out as an exercise. Two functors from the given input to the images under the right functor of this guy.
Is this always the case that adjunctions correspond to deduction rules in type theory?
No, one cannot say it in that generality, but it's certainly the case that, so due to this tight relation of some kinds of categories to type theories as being their categorical semantics, one can then go and say, well, that's a game people keep playing, but it's not a fully formalized game. But you can take any kind of category and ask what is it's called the internal language. Can I write down a type theory that embodies this category with its universal properties? And then people will try to make this happen. This is not completely, one has to, I don't know, this is a bit of a more of an art maybe than just deduction, but yeah. I mean, these days people write type theories for all kinds of categories, for double categories, for using these kinds of categories. Right. So where were we? So this was an example of basic type formation rules, how to get from old types to new types, and a category such as type now that allows these structures that had such a functor cross L for each L and such a functor bracket L for each L, satisfying this adjointness relation. This is called a Cartesian closed category. Cartesian refers to the fact that this is like the Cartesian product of sets, and closed means closed refers to this is called closure, the existence of these internal homes. Okay, so let's just boost this a bit more. This was kind of the most basic example. Let's bring in the dependency, and now I don't want to speak too much about universals, but I put it on this. I put it on this slide, and it's sort of maybe just for fun. Actually, I mean, this is a bit of a subtle topic, but we can. I don't really need to be talking about universals at all in this lecture. I just need to talk about dependent types. But it would be kind of a shame not to mention them at this point. And also, it's a good occasion to amplify how cool this rule is. That everything you ever encounter should be assigned a type. So we talked about. We said how every datum has to have a data type, and I gave some impression at least of what it means to give something a data type. You kind of know how to construct it, how to eliminate from it, how to read out of it. But now, so what is data types then? Did we just introduce a new concept? And so we should go and say, yeah, a data type is a datum, right? If I ask you what data type does this have, and you tell me, well, apparently you gave me a piece of data because now I know it. Previously I didn't. So then I should ask, well, okay, what data did I just receive? So data types themselves should have a data type. Right? They should be of the type data type. And that makes it, so if you're naive, you want to say, well, okay, what do we have? So for instance, L is a you want to say, okay, let there be a data type called type. Data type. And then you're going to say, well, type itself, it should be a data type, so you would write something like this. But in the semantics, which maybe I should mention now, I think I have it somewhere on this slide. So if we interpret this, for instance, in a category of sets, of course, it's something like every set is a set, but then you want to say the collection of all sets itself is a set. And that, of course, leads to paradoxes. So we don't do that, but there's ways to get around this by stratifying your type universes. So instead of talking about all data types, we talk about all of them that are small in some sense, that are not too large. And we maybe write an index subscript I here, maybe I runs over the natural numbers or some other index set, and we say type 1, subscript 1, is the type of those data that are just small. And then the data type of all small data is then itself the data type, but it's large now. You say it's itself actually of data type 2, and so on. So this is an ancient idea that was one of the original ways of Grothendieck actually to resolve Russell's paradox in a categorical motivated from category theory. He introduced something called Grothendieck universes to speak about a set of sets, which you frequently like to do. Say, well, you need to say, what does it mean to have a large set of all small sets? So you ask them to be sets that behave like universes. They are closed under the transitive. So for instance, all elements of it correspond to some set. And for instance, the union of all these sets that are elements of the universe are also part of the universe. So it's somehow closed under the usual operations that you want to be doing on sets. But it's still a set and not a class. And that's the same thing one can do with types. So if we just agree that we have a vague feeling of how this evades a paradox, we can go and say, well, data types D now are of some type. And that allows us, for instance, as I just mentioned before, to have programs that output data types. You can have a program that computes a data type. This is indicated here. It reads in a gamma, and the output is a data type. And it can compute data of these dependent data types. So this is really what we're going to be interested in. Suppose you have a program that reads a datum of type gamma, a datum of type I, which itself may now depend maybe on gamma, and then it outputs something of a data type that may actually depend on one of these inputs. So what this means in our category theoretic translation to the category of data types is that these dependent data types are now vibrations over gamma, and these programs that assign dependent data are sections of these vibrations. I'm not sure if that slide that I'm showing you actually shows what I'm saying, but let me write it here. Think of gamma as a set of points, and then if we have now a vibration, so just a surjective map from another set D to it, then it just means that D depends on gamma in the sense that if you pick a gamma in here, this is the point, right? The singleton set, unit type. So it picks one of these elements. So it just means that, well, you can pull this back here. So there's that part of the set D which sits over here on the D gamma. Right. So in other words, D is, if you're just talking about sets, it's just the union of a gamma of the D gammas. Right, so the way to parameterize that one categorical language, that one data type depends on another, we can say that it's fibers over, and then to say that now we have datum, so we want to say something like given gamma and gamma that we produce a P depending on gamma, a datum which takes no value in a fixed D, but in a D that also depends on this gamma. So this is the way people write, and it's programming language type theoretic notation. So this in the category theory now just means that our program is not just a plain map, but it's a section. So I'm omitting the extra I that I had there for simplicity. I'm saying, okay, here's our output datum D, fiber over gamma, and our program takes gamma to D, but such that it's a slice map that this respects the maps to gamma, right? What this means is, if you think about it, if you start with the gamma here, you send it over to somewhere, but this diagram needs to commute. So this somewhere needs to have the index gamma, which is the gamma you started with. So it says precisely this, that gamma needs to be sent to a P of gamma, which takes values in that fiber of D over gamma. That makes sense?
So the projection P would be a program that for every type, in the pullback.
Yeah. Sorry, I see. If this was P for program, let's give this another name. This is another P. Let's just call it. We don't have to give it a name.
So this would, if you think of it as a program, it would be a program that given the D gamma, it spits out the gamma, exactly. Gamma on which it depends.
Yeah, exactly. Given a kind of parameterized datum, compute what is it parameterized by, or just it's not a big computation, so it's just extract that information. Exactly. So you see, this is an important step here. That it's also in category theory an important step that it's one of the things where the simulated of categories, it starts showing its power, even though it may not be. I mean, if you've seen this for the first time, maybe it may not be evident yet, but this is actually a powerful construction. So we started with a category, and we understood its morphisms as programs, and then we realized that whenever we have an object in a category, we get a new category called the slice. The category whose objects are now the original object equipped with a map to your given object, and the morphisms now are the maps between the domains that make the corresponding diagrams and commutes. It's those maps that kind of respect vibration over a given base. This is called the slice category. This is a Homotopy slice category. Slice over gamma. And it's an important insight of category theory that you can kind of learn about a category by looking at all its slices. And here in type theory, we see the analog. We kind of see, well, if we have these data types, we can look at all the data that depends on these data types. Let's see where we. So here, this diagram further explains how this relates to type universes. Maybe that's not. Maybe we can get back to this. So yeah, let me just say, if you interpret this in sets, so if you say that our category of data types is just the category of sets, which is a simple model of a category of data types, maybe the most naive, the default model. Default in the sense of the tautological model, if it's not the one we mostly actually use in practice. Could take this to be a Grothendieck universe, so it's a big set that indexes other sets, and that would be the set of these sets equipped with a base point. So we have a set of sets. You can form the larger set whose elements are pairs consisting of one of the sets in the original set and a choice of point in there, and maps. Yeah. And so this is the map that forgets this base point. And then one can see that every small vibration, so whenever the fibers here, all the d-gammas are I small, are part of the set, then there is a classifying map here that it's just a map that you see. This is not a mysterious thing. So this is what I'm calling here name of D. So gamma name of D to start I. If RD is the one on the left, it's just a thing that sends. It's just as a map of sets now on the category of sets. It's just a function that takes gamma to D gamma. It's just a fiber assigning map. And any vibration is such. Anyway, so this is, I mean, it's maybe not too important at this point. So this is relation between vibrations. And now an important point that will get us to first order logic. This will really be the anchor point, crazy as it may sound, to understand quantum logic and then the quantum measurement, is actually to generalize our type formation to these parametrized contexts. So suppose now, let's see, should I do it on the board or can we still, let's see how far we get on the slide. So remember previously, so I want to now show the two most important type formation rules for these dependent types, where everything may depend on some parameter. And remember there was pair types and function types, and they were themselves created from a pair of data types. So suppose now this pair of data types, it's self-dependent. So suppose that instead of just having, so previously we had L, can I point to something actually? Yes. Over here, everything. Yeah. Right, previously we just had an L of type L and an R of type R. Now suppose that the type of this R may itself depend on L. So then the pair L, R is actually itself an element of this dependent coproduct, of this coproduct that did I say this before? Let's see, am I getting ahead of you? No, sorry, I'm saying this wrong. I hadn't introduced this before. So we want to, let's see, I'm pointing to the right, left here. So suppose we have a data type, so not just a fixed R, but R depends on L. And then we want to declare, sorry, I got ahead of myself here. We want to declare, what does it mean to have a pair, L, R, where L is some L, and R is some R, but now R itself depends on L. So we say, well, L, R is not just in L times R, But in this coproduct, think about it in sets. This is just what happens. You take the coproduct of all these RLs for each point in L, but the RLs may differ. Well, it's constructed as before. Remember, the pair type was just constructed by saying, well, take a datum of the first type and of the second type. And it's the same thing here. Take a datum of the first type, of the second type, only that the type of the second type now depends on R. The same here, we want to form what's called the dependent function type. So you want to say what is an F that is in the product of all these RLs. So for each, this means it's like a function for each L, you want to, the F should somehow determine also an element in R at that L. Well, that's what you get from a function from L to R. So if one goes through this, maybe I'm going a bit fast now here, but if one goes through this and asks what is the analog of the construction rules, one sees, let's do this on the board maybe, one sees that the plausible conditions on these rules is that these operations of what's called dependent sum or dependent coproduct here and dependent product form an adjoint triple. And let's do that on the board. How am I doing with time? If I'm asked, I haven't checked. Here's a clock.
Here's about half an hour.
Half an hour. Okay, very good. So let's do that carefully because that is important. Maybe I'll remove. Maybe I'll. Half an hour is good. So let's do this, and then the VKH isomorphism here, and then we have a good ending point. So let's do this in sets. So let's get a handle on this. So let's take what we're doing now. Let's take type in the category of sets. Just a very elementary category theory. And so then let's look at, let me still write type just to put us in the right mindset here. Right, it's the category of sets, right? Sets and functions between them. Sliced over gamma. So there was this category of elements of maps to gamma and morphism of these triangles. And here's our plain category of sets. So there's three functors now, first of all, and then they're adjoint excessively. So this functor is just the context extension which forms the trivial gamma fibration. So let me write it in. So if you're copying this here, I'll write down something which I'll then erase to make room for something. So maybe you want to leave some space. I'm just finding this now. So this takes a set and takes it. We need, in this category, objects are morphisms and hence are mapped from somewhere to gamma. So it takes it to the projection map from the product S times gamma to gamma. Let me put brackets on it to indicate that this is one object in this category, right? So this notation is slightly abusive, right? Total space is this Cartesian product equipped with a projection map. As a map, I should call it pur to. It's the projection on the second factor. So as a dependent type, this is the independent type, right? Remember these fibrations here. This happens to be a fibration. Remember that its fibers we think of as being data types indexed by gamma. But the fibers of this thing are always S. So for each point in gamma, the fiber is always S. So that is S as an independent type regarded as trivially gamma dependent. And for this reason, this is called context extension. Because S remains an independent type, but nevertheless, gamma is now in the context. Other things can depend on it. So that's a trivial construction we can have. And then the claim is, well, there's two other functors now. They go back, and that are the left and right adjoint to that one. And this one here is the coproduct over gamma. And I should warn you, so our category theory is called the coproduct in type theory. For the most bizarre reason, you would think that in type theory people are sensitive to the typesetting, but they call this the sum, which is something I want to absolutely avoid because of course you can do this once when you're always only talking about sets where sums don't actually exist. You can abuse the notation sum for sums. But we're going to be talking about linear types in a moment where sums actually exist. I don't want to abuse that symbol, but just okay if anybody looks this up in the literature, gets confused. So the coproduct functor just takes the total space. So this functor, maybe let me write it like so, let me write it here. So it's coproduct x by gamma. So what does it do? It takes a fibration of D over gamma, and again, I will delete this if you're copying, leave some space. I'm just indicating what this map does. What does it do to it? Well, so this is a type fiber or a set fiber or just map to gamma. Well, where do we take it? Well, we take it to just D, just its total space. Well, why does it have, if it just takes it to the total space, why does it have this funny name co-product? Well, I think this is actually the equation that I just erased here. If we think of D over gamma as being, as we do, if we think of it as being a gamma index type, so then we want to think of this D as just the union of all its fibers, right? This is gamma, if we know it sets of all the D gammas, right? Literally, right? Should we draw a picture? So here's 3 points. This is S, this is gamma. And here is D. D might be like 2 points here, 3 points here, and nothing here. Well, okay, let me not write nothing, it's so hard to draw. We write a single thing here, right? So D is the set that consists of 1, 2, 3, 4, 5, 6 points, where these 2 map to this one, right? These 3 map to this one, and this one maps to this one. So then this here, these 2 points are D, so let's call the points A to B, A, B, C. So this is DA, right? This here is D, B, this is DC. The union of them is just D. So in this way, the total set is just the union. And that's why this functor is called the coproduct. It takes the disjoint union of the fibers. Okay? And I'm going to just erase this and draw the other functor. Maybe I'll also erase this here. And yeah, and so I just claim this is left adjoint. Easy exercise. You can do it maybe in the coffee break or something. Let's try to get to the end of this slide here. And then here's the product. Gamma. Well, as the name suggests, this will take the product of the fiber. So this will take our D fiber over gamma, just mapping to gamma to product indexed by gamma of the fibers D gamma. You see, if D happens to be not dependent on gamma, this is just the gamma fold product of gamma, which is just a function from gamma to D. And this is, so in this sense, this generalizes the previous function term. In this sense, in this way, products and co-products over these index things are captured by this diagram. And they're adjoined in this form. And now let me close by saying, so we'll be using, so this is important. Maybe I did this too quickly, we can maybe do it tomorrow again. Let's see what happens. So we'll be this diagram and its generalizations will kind of drive the whole rest of the course. We're seeing what happens to this diagram as we add quantum effects. But to get more insight into this diagram, let's just see what it does. What this has to do with logic and with VHK interpretations. It was mentioned at some point. So let's look at one further data type. From the data type perspective, we want to ask things like, what are certificates for certain properties? So this is actually maybe the most, or one of the most immediate application points for type data. We want to have a program that together with its output produces a certificate that the output adheres to specified rules, that it actually obeys. For instance, it might produce a floating point number, and we want to guarantee that the floating point number is really within the specified epsilon of the correct value. So then we want the program to also output that certificate, so which means it has to output a datum which is either true or false of a property. So how do we do this in the categorical semantics? What does it mean? Well, it turns out that properties are encoded by those vibrations or those maps that are monomorphisms whose fibers are either empty or single. Right? Suppose we have a proposition about data of type gamma. So any piece of datum here either satisfies this proposition or does not. So we're asking, is this proposition true for this datum or not? Is it accurate with an epsilon or something? And so we can form a subtype, which in set theoretic language, what this generalizes, is the subtype of those gammas that satisfy that proposition. Kind of a tautological construction again. But you see, it's now a dependent type, dependent on gamma, which is either the empty type or the singleton type. So either it has datum or not, depending on whether the proposition is true or not. And that is a translation from logic, from propositional logic. It turns proposition, or a set in this case, to an object in our slice category. And now we can see that all these operations, all these type forming constructions that we introduced, they all correspond to the most elementary constructions in first propositional and then first order logic. Namely, let's look at the product. So suppose we have two such propositional types and we form a pair type. So the interpretation should be datum of that type should be a certificate that both P1 and P2 hold for our given gamma. So that means we want to form the product, but we now form it in, everything depends on gamma. So we form it actually in the slice category. And if you think about it, if we are we're in gamma and we have one, we're in the slice over gamma, we have one proposition P, so this is a subset, and we have another subset here. Then the Cartesian product in the slice category is actually the fiber product, is the thing that in calligraphy language might be called E cross over gamma 2. So the fiber product is that map over gamma, which over a given gamma contains the products of the fibers here. But the fibers are either the empty set or the singleton set. And the product of that is empty if either is the empty set, is the singleton, if both are the singleton, which is the logical AND operation. So the fibers here are inhabited if and only if both of these fibers are inhabited. So in this sense, the times operation here is exactly the logical AND for our gamma. So this is the type of certificates that certify that gamma satisfies both P1 and P2. So by the same logic as an exercise, maybe you can verify that if you take the coproduct here, that course, so it's like a 2-point index coproduct. This holds the certificates that either P1 or P2 hold. There's some truncation business here, which I'm maybe glossing over now. And then interestingly, so this is propositional logic embedded into the type theory and into the category theory thereby, but also the first order logic, the quantifiers are now reflected. So let's look at this. Let's look maybe at this example. Remember, it was taking the product of all the sections. So suppose we have a proposition here, and now we're forming the product of all its fibers. So each fiber is either empty or inhabited, depending on whether this is true or false. So if we take the product, it's either empty if any one of them was empty, or if and only if all of them were singletons, the product is the singleton. So this means the resulting type is non-empty if and only if the proposition actually held for all gamma. So this is the all quantifier, and this is the substantial quantifier. There's implies there. Okay, I think I'm out of time. Maybe we're out of energy. This is the classical story of classical data, classical languages, and classical logic. And our goal in the next course lecture will be to bring in a little bit of linear quantum data. Yeah, maybe I'll stop here. Thanks.